Hello, this is Dr. Gardner. We're going to be looking at how to predict how cations and anions combine together to form ionic compounds and how to write their formulas today. First of all, I'm expecting that you've already watched our videos on classifying elements by using the periodic table and that you have a periodic table in front of you that you can use for reference. I also expect that you've already watched our videos on writing the formulas for isotopes and ions, and that you realize as you write your charges, they're in the upper right hand superscript of your ion formula. So we're going to be looking at that. First of all, let's talk about ionic compounds and let's define what a compound is. If we have a compound, we're going to be having a pure substance that's composed of two or more elements that have been combined chemically, and they're always going to be present in definite proportions with respect to the number of atoms present. For example, if I have the elements of iron and sulfur that have combined, I could have iron pyrite, which is also known as iron 3 sulfide. In this case, where we have our definite proportions, we have 2 iron cations and 3 sulfide anions. So we have that very definite proportions of 2 irons for every 3 sulfurs present in the formula. So if I have a pure substance as a compound, that's what I would expect. The other key category for a compound is that you must have 2 or more elements combined in these whole number ratios in that pure substance. So here we have 2 elements, we have iron and sulfur. Now I want you to realize the properties, though, of compounds can differ quite a bit compared to the elements that have been combined to form the compound. For example, if I have elemental iron, which has not formed a cation yet, has not lost its electrons to form a positive charge, and if I have sulfur that hasn't formed sulfide yet, meaning it hasn't gained electrons to form a negative charge, their properties are very different. If we have sulfur, we have a non-magnetic yellow powder here from the non-metal. If we have elemental iron, we're going to have a magnetic material from the iron. When they form to form their compound, the iron pyrite, it looks quite a bit different, and it would no longer be attracted to a magnet at that point. So we can see that's definitely very different characteristics. Like, in fact, when I have a compound, I cannot separate the elements out with a physical process, like using the magnet or solubility or differences in melting points or boiling points. The compound is a pure substance. The only way to separate the elements back out of a compound would be through chemical reactions. We'd have to force the electrons off of sulfur and back onto the iron to form elemental iron and sulfur back again in a chemical reaction. You can't do it with a physical process. However, if I have a mixture of elements of iron and sulfur, in that case they haven't formed a compound yet. We can separate them with physical differences in their properties. For example, since the iron is magnetic and the sulfur is not, I can easily separate the iron out with its property of magnetism from the sulfur. Okay, so that's important to note. Compounds are going to be chemically bonded together. They can only be separated chemically, and there's nice whole number ratios of the atoms that have combined, and their properties are very different than the separate elements before they have formed the compound. Now, we can have molecular compounds. This is an example of an ionic compound that had ions present, which is what we'll focus on today. But starting in the next chapter, we'll be looking at molecular compounds. Our molecular compounds are going to have nonmetals or nonmetals and metalloids that have combined, and those nonmetals, when they combine, instead of transferring electrons to form ions, they actually will share their outer electrons to form what we call covalent bonds with the nonmetals. So we can have groups of 2 or more nonmetal atoms combined together by overlapping their outer orbitals of electrons, sharing those electrons to form compounds as well. When we have metals and nonmetals, or when we have cations with anions, we have transferred entirely electrons rather than sharing them to form ions. And so those are 2 major categories of compounds you should be familiar with. Today we're going to focus ionic compounds, though, and see how we can look at the ion charges and relate that to the simplest empirical formula, the simplest formula with the ratio of charges to balance charge out to 0 charge overall when we write their formulas. So let's consider if I take 2 elements again. So I have elemental pure substances here with just one type of element present in their substances. We have sodium. We also have the diatomic element chlorine. So diatomic chlorine in the gas phase. These are still elemental substances even if there's multiple of the same atom present in a molecule. It's still an elemental molecule. It's not a compound. We haven't combined it with any other element. Now, if I take a piece of sodium and put it into the chlorine atmosphere, it's going to react quite violently. Now, I want you to think about this. You would never want to consume metallic sodium. It's going to react very violently with your body. If we throw it just in water, sodium will react violently with water, and it will end up basically giving up an electron for each sodium atom to form the sodium cation. It forces those electrons onto the water molecules, and it displaces hydrogen gas as part of that process, while it forms sodium oxides and sodium hydroxides. So the solution starts to become basic because of the sodium hydroxides and sodium oxides that are dissolving in it. And then we end up with the hydrogen gas released. That process is very exothermic. We release that hydrogen gas, that energy from the exothermic process, that heat released, ends up potentially igniting the hydrogen gas in the oxygen atmosphere, and it can explode. Okay, so very dangerous metal because of its reactivity. We usually store it under mineral oil, or you can store it under kerosene. We usually will store it under mineral oil here in the chemistry department to prevent it from reacting with water in the atmosphere. Okay, so very reactive metal. You wouldn't want to eat it, right? Okay. Now, chlorine gas, you wouldn't want to inhale chlorine gas because it likes to form chloride ions by stripping electrons off of other atoms. So if you inhaled it, it would cause chemical burns to your lung tissue because it's actually stripping electrons off of your atoms and molecules in the lung tissue to react. And then it forms chloride ions. Okay, but the elements are very reactive to begin with. If I put them together, well, the sodium readily gives up electrons, and the chlorine would like to gain electrons, so that's a very exothermic process. So we can see light energies released, we get sparks, we actually start to see a white residue forming on the flask where we've mixed the two of them. So we get all this energy release, we're forming a new substance here, that white substance forming on the glassware. That's actually a new chemical compound. It's a compound because we've combined two elements, so we have to have at least two or more elements combined in whole number ratios to form compounds. Our whole number ratio here is 1 sodium to 1 chlorine, so we form sodium chloride. Now that's common table salt. Okay, so we form common table salt. Now that you can notice that the compound formed from the elements has very different properties from the elemental sodium that was so reactive and the elemental chlorine that was so reactive. The sodium chloride you feel very comfortable putting on your French fries from your favorite fast food restaurant and eating a small amount of it. Your doctor may recommend not consuming too much sodium chloride, but it's not because he's worried about it giving electrons to your atoms or molecules or stripping them off of your atoms or molecules to cause chemical burns. Mostly they're worried about high blood pressure and dealing with all of those ions in your body as you excrete them. But here the sodium chloride is much less reactive, much safer to consume and interact with. Okay, so compounds can have very different properties from the elements they have formed from. This is why your instructor will be very unhappy if you try to show the formula for an ion and you forget to show the charge. Because if I don't show the charge on a sodium cation, or if I don't show the charge on a chloride anion, when I have them in my chemical reactions, well then I might assume that I have elemental sodium or elemental chlorine, and in those cases their reactivity will be very different. They haven't lost or gained electrons yet. Okay, so the charge is very important. Now it is acceptable when you combine cations and anions together into a chemical compound formula to not show charges, but only if the formula indicates the overall charge of the entire compound formula is 0. Now that would occur because I have a sodium with a +1 charge and a chlorine with a -1 charge. If I add up the +1 and the -1, it adds up to 0 overall. So I don't show the charges with the combined ionic compound formula here. It's understood I balance the charges. If I showed either ion by themselves, though, I must show the charge to indicate that the sodium has lost electrons to form a positive cation, and your chlorine has gained an electron to form a negative anion. Okay? So as we're looking at ionic compounds, the key thing to recognize in your ionic compounds is you're going to have a cation and an anion. So we usually write the cation first and then the anion second as we're beginning to write ionic compounds. Some more advanced applications might break that rule, but don't worry about that right now. Now, I could have monoatomic ions in my ionic compound formulas or polyatomic ions. A monoatomic ion indicates mono for 1, so I have a single atom that has formed an ion by gaining or losing 1 or more electrons. Okay, so that's like the sodium cation. It has lost one electron. It's a single atom that has done so, so it's a monoatomic cation or a monoatomic ion. Now I can have polyatomic ions. Now polyatomic ions will have a group of several atoms combined that will have formed an ionic charge. That group of atoms are chemically combined together, and they can go ahead and gain or lose as a group one or more electrons to either form a cation or an anion. So we'll be seeing some of those in the next chapter. An example of a polyatomic ion would be a nitrate ion or a chlorate ion, and so we'll learn to predict polyatomic ions like oxoanions, where we have a nonmetal combined with oxygen in a group with several atoms where we have formed an ion by gaining electrons to form an anion in those cases. Okay, so you'll be seeing that later, more polyatomic ions. Today we're going to focus mostly on monoatomic ions, but when I do combine my cations and my anions in my formulas for ionic compounds, we need enough cations that their overall positive charge would balance the overall negative charge from the anions in my formula. So I need to get the simplest whole number ratios of the cations and the anions so that their charges in the chemical compound formula add up to 0. So we'll be doing that today. Now first of all, realize when we have cations and anions, well, we have positive charges attracted to negative charges. When we actually have ionic compounds, they don't exist as molecules. They actually exist in what we call an ionic lattice. We have our cations and anions maximizing charge attractions in the ionic lattice as they stack together. And then we have my repulsions of like charges of cations with cations or anions with anions minimized with their positions in that ionic lattice. So I really don't have a discrete unit like we see when we write the ionic compound formula. That's just the simplest ratio of the cations to anions. We actually have a whole bunch of cations, a whole bunch of anions all stacked together to maximize charge attractions and minimize charge repulsions. Okay. So we don't expect ions to usually exist by themselves. So I won't have a cation usually by itself. It usually will have an anion nearby to maximize that charge attraction. It takes energy to separate those ions from one another, and so this is why I expect them to be in groups to maximize charge attractions. So if I see a cation somewhere, you should be saying, well, where's that anion? Or if I see an anion somewhere in a formula, I should be saying, well, where's the cation? Okay, they come in groups that balance charge, we would expect, in the overall ionic lattice and in our simplest ratio formulas we're writing for ionic compounds. Okay, so let's practice writing some ionic compound formulas. First of all, you need to be able to predict the charge on ions based on their position in the periodic table. This is why it was important that you've already watched our previous videos on classifying elements in the periodic table, as well as writing ionic charges for elements that we predict to only have one possible ionic charge for the monoatomic ions. So we looked at that in our last two videos. So if you haven't seen those, you want to go back and watch them before you watch this portion of this video. First of all, if I have sodium, when sodium forms an ion, I need to look at what type of element it is. It's on the left-hand side of the periodic table. Okay, so it's a metal. Hydrogen would be the one exception for that. It's a nonmetal. But in group 1, sodium's present. So that's column 1 or 1A. So look on your periodic table. We predict that's an alkali metal. So sodium, in fact, all of the alkali metals, sodium and lithium and potassium, rubidium, cesium, francium, we expect them all to only lose one electron as they form a cation, because that will give them the same number of electrons as the nearest noble gas before them. So I expect that sodium will lose one electron and form a sodium cation. That's a +1 charge. Okay, so let's write the formula for the sodium ion. We'll always indicate the charge as a right-hand superscript. If there's only a +1 charge, we just show a positive symbol. If we have a charge greater than 1, we would show a 2 or a 3, then the positive sign to indicate whether we're positive or negative with the charge. So here I have sodium with a +1 charge. So there's my symbol for sodium. Now let's look at the element it's combining with. It's going to combine with chlorine, and chlorine is in group 17 or 7A. Okay, that's on the right-hand side of the periodic table. It's one of the halogens. They're nonmetals. Those halogens or nonmetals, such as chlorine, will form monoatomic anions by gaining one electron. That allows them to have the same number of electrons as the nearest noble gas. So it forms the chloride ion with a -1 charge. So I write the element symbol with the charge as the upper right-hand superscript. If I don't show a number with the charge, we assume that it's 1. So I have a 1 negative charge here. Okay, now when I combine sodium with the chloride ion, we want a balanced charge to have a zero charge overall with the simplest empirical formula, simplest ratio of the ions in my ionic compound. So if I write the formula for sodium chloride, which is common name is table salt that you might have in your kitchens, we would write NaCl. I need one positive one charged cation and one negative one charged anion to balance charge, so I have one of each. Once they're combined together, we have an overall charge of 0, so I shouldn't show the charge anymore at this point. This is my formula for the ionic compound of sodium chloride. So if you're thinking about how many of each ion I have, I only need one of the positive sodium cations, one of the negative chloride ions. They combine in a 1-to-1 ratio to add up to 0 charge to give the sodium chloride formula. Sometimes it's useful, especially as we get to more complex ionic compounds, to set up some tables to look at the number of ions we have and their overall charge and make sure we're adding up to 0. So in this case, you probably didn't need to do that, but let's just practice it. Let's say we have a table with our cations that we have present. We're predicting one cation. So it's a sodium cation with a +1 charge. So my total charge for all the cations I'm predicting are in my formula is a +1. Then I'm going to set up a second column to predict my anion charges. So my chloride ion is a -1 each. We're predicting we only need 1 in our formula, so that adds up to a -1 charge overall. And if you add up all the charges, we add up to 0. So my anionic formula that I have should have the total number of the cations and anions combined to add up to 0 charge overall, and then I don't bother showing a charge on the ionic compound formula. So let's look at some other scenarios. If I have the potassium ion, we want to write the symbol and charge for potassium. Now I wouldn't write a P for potassium. That would be reserved for phosphorus. So you must remember that the potassium symbol comes from its old-fashioned name kalium, and so I'm using a K, and it's an alkali metal just like our sodium was. So it's a +1 charged cation. It's in group 1, right, the alkali metals. And then if I combine it with an oxide ion, well, oxygen, when it forms an ion, oxygen is in group 16 or 6A. It gains 2 electrons to be like neon, to have the same electron configuration as the noble gas neon. So we predict the charge on the oxide ion to be a 2-. Since it's not a 1, I write the 2, then the sign of the charge. Okay, now in this case, I can't have just one cation and one anion to balance charge. I'm going to need to have multiple of the potassium ions. So let's consider that. To write the chemical formula for the ionic compound of potassium oxide, we would have 2 potassium cations and 1 oxygen atom. And that's because when we look at them, if I have 2 potassium ions, I have a +2 charge overall. I can indicate that with 2 before potassium, before they've combined. And then if I just have 1 oxide, I don't usually show the 1, but we can imagine it's there. They combine in a 2-to-1 ratio. So once they combine to form the ionic compound, I show a subscript 2 after the cation to indicate that I have 2 of those cations present in the compound formula. When they haven't combined yet in the compound, we'd show the 2 as a coefficient before the ion. So if I set up my tables in this case, I could see that I need 2 potassium cations with a +1 charge each, adds up to a total of +2 for all the potassium ions. And then I need 1 of the oxide ions with a 2- charge on each oxide, so there's a -2 charge total from the anions. If I add up my charge totals from cations and anions, we see that we end up with an overall charge of 0. And I can easily see I need 2 potassiums, so I should write the potassium formula with a subscript 2, and then oxygen has no subscript shown. I only need 1. We don't show a subscript when there's only 1 of the ions, because if we don't show 1, we assume that it's 1. Okay, so in my mind mentally I'm thinking there's a 1 there even though I don't need to write it. Okay, let's try another one. How about we look at the lithium ion? Now, you should be getting used to looking at the alkali metals in group 1 or 1A. Those alkali metals all have a +1 charge. They're losing 1 electron, so I expect lithium is Li+. My charge shown is the upper right-hand superscript. If I look at the sulfide ion, well, sulfur, just like oxygen, in fact, oxygen and sulfur are in the same family, in the same group, in the same column on the periodic table. So that group is group 16 or 6A. So sulfur will gain 2 electrons, just like oxygen wanted to gain 2 electrons to form the sulfide ion. and so we end up with a 2 minus for the charge. So if I write the formula for lithium sulfide, this is very this is very similar to when we had potassium oxide. So I have 2 lithium cations would have to balance the charge of one of the sulfur anions because the charge is twice as great and negative for sulfur compared to the lithium's +1. So if I write how many ions I have of each in the formula, I could say, well, 2 lithium cations combine with 1 sulfide anion to form my lithium sulfide ionic compound. And I show a subscript 2 to indicate 2 lithium ions have been combined here. Since the overall formula is neutral overall with all of the positive and negative charges, I don't show any charge on the overall ionic compound formula. If I set up my table to keep track of my ions, we could write 2 lithium cations with an overall charge of +2. And we could say 1 sulfide anion with an overall charge of a -2. If I add up the charges from all my cations and all of my anions, I could say my overall formula charge was 0, which is why I'm not showing any charge on the lithium sulfide ionic compound formula. Okay. Now we're going to look at a couple that are just a slight bit more challenging than this. So let's consider what if we have a magnesium ion. Now magnesium isn't in group 1, it's in group 2. So my second column on the left-hand side of the periodic table, it's still a metal because we're on the left-hand side of the periodic table, and it forms a charge equal to its column number. So it's group 2, it forms a charge of 2+, because it loses 2 electrons to have the same electron configuration, the same number of electrons as neon. So magnesium forms a 2+ charge. Well, let's look at sulfide again. So we already predicted that sulfide, just like oxygen when it forms oxide, gains 2 electrons. So I write the element symbol and the charge as the upper right-hand superscript is a 2-. If I'm predicting how many I need of each of these ions to balance my charge overall, you should realize I just need 1 of each. Okay, so I could write the formula for magnesium sulfide. It's just 1 magnesium cation and 1 sulfide anion. Adds up to 0 overall charge. So I have a formula like this. We're thinking in our heads there's a subscript of 1, but I don't need to write 1s as subscripts. I only need to write a number for the number of ions when it's 2 or greater. We assume if it's not shown, it's a 1. So if I really look at this combining, we're thinking, okay, I have 1 magnesium cation with its 2+ charge, 1 sulfide anion with its -2 charge, combining to form a neutral ionic compound forming a ratio of 1 to 1. Now we really don't have just discrete magnesium sulfide units that are separated from all the other ions. We actually have a whole bunch of magnesium cations, a whole bunch of sulfide ions, all combined together in an ionic lattice, maximizing charges between cations and anions. This is just the simplest ratio of the ions we're looking at with the ionic compound formula. The actual structure is more complex. If I were to set up my table to keep track of the ions in this case, well, the magnesium cation with 1 of them will give me a total charge of a +2. My sulfide anion with its -2 charge gives me a total charge of -2 since I only have 1 of each of the ions, the cation and the anion. The overall charge will combine to be equal to 0. Okay. Now these tables will be useful as we get more complex ratios of cations to anions. So let's consider the calcium ion. Now the calcium is right below magnesium in the alkaline earth metals in group 2 in column 2 on the periodic table, or 2A. So if we look at calcium, it will lose 2 electrons to have the same number of electrons as argon, which is the noble gas before it. Okay, so it gets a 2+ charge. Let's combine it with bromide. Now bromide again is in group 17 or 7A. It's one of the halogens on the right hand side of the periodic table. It's a nonmetal, so we expect it to form an anion. And it will gain 1 electron to have the same number of electrons as krypton after it, the noble gas after it. So we end up with bromide having a -1 charge. So if I write the formula for calcium bromide, well, the formula for calcium bromide would require 2 bromide ions to balance the charge on the calcium cation. So I'd write the calcium cation. Since there's only 1 of them, I don't have to show the 1 as a subscript, even though I'm thinking that it's there. And then I have to write a Br with a subscript 2. The subscript 2 tells me 2 bromide ions are present to balance charge. Since the overall ionic compound formula is neutral, we don't have to show a charge for the overall formula. So what's really happening here, if we write this out as a reaction, I have calcium combining with 2 bromide ions to form my calcium bromide ionic formula. Or if it helps you visualize things, you can set up our tables and we can say, okay, I have 1 calcium cation with an overall charge of a plus 2 for all the cations. I have 2 bromide ions though, so if I add up a -1 plus a -1, I get a -2 charge overall. And so my overall formula charge is equal to 0. Let's consider if we have the aluminum ion. Now aluminum is going to be present in column 13 or 3A. Okay, it's right below boron. It's right underneath the metalloid line. It's treated as a metal. So the aluminum ion, though, will lose 3 electrons. It always forms +3 charged cations, as we have talked about before in previous videos. And it ends up with the same number of electrons as neon before it, as it forms a 3+ charge. So we're seeing that some ions can have higher charges, and so we'll have to be careful as we're writing formulas. We're keeping track of what's going on with charges. So here we have a 3+ for the aluminum cation. Let's combine it with selenide. Okay. Now if you remember, oxygen as it formed oxide and sulfur as it formed sulfide both ended up gaining 2 electrons to form their anions. Well, selenium, right below oxygen and sulfur, in the same group, in the same family, in the same column, does the same thing. It gains 2 electrons to have the selenide ion form, and that selenide ion as it forms has a 2- charge, has the same number of electrons as krypton after it. So we end up with selenide with a 2- charge. So if I'm predicting the formula here for aluminum selenide, your table might be pretty helpful to write to keep track of all the charges. Once you get really comfortable with it, you might be able to predict that its formula would require 2 aluminum cations and 3 selenide ions. If you can't visualize that in your head without writing the table, you should write your tables out. But what's really happening here is we have 2 aluminum cations with a +3 charge each, and we have 3 selenide ions with a 2- charge each. We'd have to have 2 aluminums and 3 selenides to add up to an overall net charge of 0, and then we wouldn't write a charge on the formula. So the other way we can look at that is with the tables I've shown you. If I have 2 aluminum cations and there's a 3+ charge each, the overall charge adds up to a +6. If I have 3 selenide ions with a 2- charge each, we could add those up. So 2-, a total of 4-, 6- for all the selenide ions, so I get a -6 charge each. So we see it takes 2 aluminum cations and 3 selenide ions to equal our positive cation charges and our negative anion charges to get an overall charge that's 0. Since I took 2 aluminum cations, we show a subscript 2 after aluminum in the ionic compound formula to indicate I required 2 of those cations. And since we required 3 selenide ions, I show a subscript 3 after selenide to indicate that I had 3 of those that were used to add up to an overall charge of 0. So the tables are more useful once you get slightly higher charges to keep track of everything more clearly. Let's consider if we have the zinc ion. So zinc, if you remember, it's to the left of aluminum and down one row on the periodic table, and it always forms a 2+ charge. I recommend just memorizing that one at this point in the course. We'll learn some rules as to why it likes to form a 2+ charge, and that's the only stable charge it forms later on when you learn how to write what we call electron configurations to look at the energy levels of electrons. But right now, take my word for it, memorize that's a 2+ charge, and that's the only stable charge that zinc cations form. So I get zinc 2+. Let's combine it with nitrogen. So when nitrogen forms a nitrogen anion, well, it's in group 15 or 5A. It would like to gain 3 electrons to form the nitride ion. Okay, because if it gains 3 electrons, it has the same number of electrons as neon, the noble gas after it on the periodic table. So if I combine the two here, we need to balance out the charges on the zinc 2+ cations, right, and the nitrogen 3- anions to form zinc nitride as my ionic compound. So in this case, I show a subscript 3 for zinc, a subscript 2 for the nitride to balance charge for my formula. Another way of visualizing this is we could say, well, we have 3 zinc 2+ cations combining with 2 nitride 3- anions. So I show the subscript 3 after zinc indicating 3 of those zinc cations, subscript 2 after nitride indicating 2 nitride ions. If I wanted to write this out with my tables to keep track of charges very carefully, we could say, well, if I need 3 zinc cations, well, there's a total of a 2+. When I add the second zinc cation, there's a total of a 4+. And the third zinc cation, if I add up all the positive charges, adds up to a +6 total overall. If I look at the nitride ion, the anion, I have a 3-, and then second nitride's another 3 minus, but that would add up to a negative 6. So I can see I need 3 zinc cations, 2 nitride ions to balance the overall charge in the ionic compound formula to get a total charge of 0. Since I had 3 zinc cations, as I said before, we put a subscript 3 after zinc in the ionic compound formula. Since I have 2 nitride ions needed to balance charge, I show a subscript 2 after the nitrogen in the ionic compound formula. Okay, so this is one of our shorter videos today. So what we will be starting next is Chapter 3. It's very useful before we start Chapter 3 if you watch some videos on YouTube on electrolytes, strong and weak electrolytes, and how they relate to strong or weak acids and ionic compounds and molecular compounds. So if you want to start looking at that before we begin lecture in Chapter 3, that would be a good thing to be doing at home. Okay, so good luck. We'll be looking more at ionic compounds and how to name ionic compounds in the next chapter. We'll also be learning how to name molecular compounds, and we'll look at how to name acids and bases and hydrates. Okay, so that's what's coming up in the next chapter. So go ahead and read the next chapter. Get ready to take your reading quizzes online, and I'll be talking to you soon. Have a great day, everybody. Bye.